All right. Hopefully everybody can hear me okay. Tried to build up some drama on the slide here. I didn't know whether you know it, but a new age of computing has arrived. The affordable personal computer, the Ohio Scientific Superboard 2. I'm trying to do this Steve Jobs style here for the first part of this. This computer, $279, 1979, was the first computer that I learned to program when I was about 11 years old. And this system was great for kids. It had easy setup involving soldering and multimeters and power supplies. It had peripherals like directly hooking TVs into like an edge connector on a motherboard. It had lethal suggestions, like you could modify your television if you wanted to work as a monitor, like so you could open it up and like change the circuitry of it. But, you know, as you know, with televisions, it might kill you if you did that. It had schematics. I mean, you could look at like how it was put together. It was just this, and then it had BASIC on it. I mean, it was just this great machine for like an 11-year-old kid. And here's sort of a picture of the one that I used when I was growing up. You would typically make like a homemade case, put your own power supply on it. I actually brought one to the conference. So it has a nice Python 3 sticker on it already. You'll notice that this is not the same one. All I'll say, if you're going to do retro computing, always better to have two than one. This is the one that I got off eBay as a backup in case I need parts. I also have to say this is the only PyCon that I have ever taken a soldering iron to, because we're gonna do a live demo tonight, and hopefully it'll work. So this is just a really fun machine for a kid. I mean, you can look inside. You could get an electric shock, which actually happened to me once. I don't think my parents knew that, but I got my finger across that and like throw it against the wall. And it was just great. So what this is a video of this in action. I kind of knew doing a live demo would be a little bit iffy, so this is what it looks like to use one of these superboards. It boots up just directly into BASIC. You see it's Microsoft BASIC from 1977, and you could write programs on it. And so the programs were very sophisticated, right? Like number guessing. Oh, okay, that's great. And then my personal favorite was binary decimal conversion, of course. So a lot of fun with that. Multiplication quiz. I mean, the thing I like about this is like the encouragement to the student there. Not quite modern there. And then the other thing is you could really like hack on this too. I mean, there are examples of like machine code. I remember having like the 6502 instruction set book kind of by my bed, you know, as like a 12-year. Maybe there's a reason why I didn't date in junior high, but it was this really cool machine. And the reason that I'm talking about this here, you might say, well, why in the hell is he talking about this at PyCon? A little backstory is that this machine sat in just the basement of our house for like 30 years, and then I went to SciPy last year, and Eric Flair, during one of his talks, mentioned something about Ohio Scientific and challengers and superboards and stuff, and I was like, oh, wait a minute, we still have one of those in the basement somewhere, and so my brother sort of brought it into Chicago, and we just plugged it in, and it still worked. Sort of amazing, you know, it's like this 32-year-old machine still works. Actually, I'm a little bit curious, how many people are older than this machine in this room? I mean, it's 1978, so it's it's okay, about a third there. Okay, so a question with this is what do you do with something like this? I mean, okay, it works. It's got a 1 megahertz CPU, 8K RAM, 8K BASIC, 300 baud audio interface. It's not really that modern. So I'm sitting around as kind of a Python programmer. I'm interested in system stuff. The really clear answer on it is that it needs to go to the cloud. I mean, that's the obvious answer on this. And the question is, like, how do you do that? This is my 2-year-old holding a cup of coffee and a sugary pastry there, you know, sort of prepared, you know, to talk about, well, how in the world would you do something like that with something like this old machine? So I sort of viewed this as like a challenge, like a hacking challenge. Of like, how would you take that, put it on the cloud? And I wanted to do it entirely with Python 3, and I wanted to throw a whole bunch of advanced stuff into the mix as well. So I'm using ZeroMQ, I'm using Redis, and there's also some 6502 assembler involved. So I'm gonna kind of take you through this whole thing. Kind of the point of the talk is actually what I hope is to actually look at some of the neat things with some of that ZeroMQ and that the Superboard is actually kind of a vehicle for doing that. So the first thing that came up is just this problem of, well, how do you actually get there? This machine had no I/O to speak of other than cassette audio ports. And what those ports sound like, I don't know whether you're going to be able to hear this or not, but it essentially sounds like a modem. I don't know whether my mic is picking any of that up, but that's what it sounds like. Just it's basically audio coming straight off of those ports. And so one possible way to do this is to essentially link it to a Mac through like a USB audio interface, and to build to try and essentially decode and encode audio from the Mac side and do like some kind of real-time interfacing. So to look into that, I mean, it turns out that this machine, it actually had a real serial port kind of hidden behind the cassette port. So it's something known as a Motorola 6850 asynchronous communication adapter. There's a standard that describes what's going on. You have to go back to Byte magazine from 1976 to find this. I'm not sure what this title. There's a title here, Computer Megalomania. I don't know what that's related to. But if you go into this episode, this issue, you'll find, okay, the report from the Byte audio cassette standard symposium, and they sort of outline, what is it that is being used on this cassette port. And they're sort of saying, one bit is 8 cycles at 2400 hertz, and a space is 4 cycles at 1200 hertz, and some framing stuff. And one other curiosity with this symposium, very interesting attendance at this thing. If you look at the article, it's tended by Bill Gates. This is like November of like 1975. So I know, how old was he? 12 or something? I don't know. Very early, kind of in the Microsoft world. So I got to thinking, about this, and it's like, well, why can't I build like a modem or something using Python? So there's a library called PyAudio that you can find. It's a Python interface to something known as port audio. And it actually lets you just access like audio line input on your Mac, on your PC. And I've actually never done anything with audio processing in Python before. So this is completely new to me. And so in my insanity, it's like, I'm going to port this to Python 3 first, and then try to use it. It turns out to be really easy to use. This is kind of what it looks like to use PyAudio. You kind of open up, create an audio object. You just open it up, you give it some parameters about how many channels, what sample rate, some buffering stuff, and then you just start reading on it. You get a whole bunch of audio samples out of it. I was amazed. I thought this was going to be really difficult to do like real-time audio on my Mac involving some huge framework or something, but it took like half an hour just to download and kind of play with it. And so using that, first thing that was done is to build a Python modem. So what this is, it was 2 threads hooked up to PyAudio, doing byte encoding and decoding, and then having that bridge to a TCP socket. So there's a couple of little pieces here, like threads, sockets, audio encoding, and this is sort of what that looks like underneath the covers. What I did is I just pre-generated samples representing a 0-bit and a 1-bit. Actually just made square waves in just like a Python array, essentially. And then to encode this stuff, you just take what you want to encode, like the letter A, you find out what the bits are, and then you just blast out that bit pattern straight to PyAudio, and it just goes out the audio interface. So that actually worked, just worked fine. The tricky case is the decoding. To do that, just to give you an idea of what's involved, you take a whole bunch of audio samples and you strip them down into essentially sign changes. So this is kind of describing that. You start with samples, you get sign bits, and then what you do is you mark the 0 crossings in this wave. That's kind of what this is doing. And once you do that, this is how you do that, by the way. You can just write a little generator function that just reads samples, and then you do some messing around with XORs and stuff, and you'll do that. And then to kind of reconstruct it, what you do is you just take all of these sign change bits, you just shove them into a sample buffer, and you just count how many ones are there. It's like each one is like a crossing of the axis. And depending on how many crossings there are, you can actually figure out whether it's a 1 or a 0. So if it's about 8, you get a 0. If it's about 16, you get a 1. And it turns out that you can do this by kind of messing around with Python's deck object is great for this. I don't know whether you sort of know this about the deck object, but it has this max len parameter. And if you use that, every time you shove something into it, an item will just fall out the other side, and you can use that to create kind of like a fixed size buffer where you just shove things into it. And so what I would do is just get all these bits, shove it in there, and just count how many crossings there were, and you have a Python modem. So this is a little demo of this in action. So this is my what I've got here. This is my Mac linked up over audio connection. So I'm running a Python 3 program as a modem. This is actually setting up a socket that I'm going to telnet to. So we're going to use that later, but I'm sort of telnetting to that. And then what I'm doing is I'm going over here to the Superboard, and this is sort of classic 1970s programming, but they had these commands, peek and poke, that were used to do anything interesting. So what I'm doing here is I sort of turned on the cassette port. And you're sort of seeing things sort of echoed at this point, like things that I'm typing on the Superboard are now coming over to the Mac. Okay. What I just did here was turn on the input. And now what's happening is the two machines are linked. So everything that I'm typing in this terminal on kind of the Mac side is actually going over to the Superboard. One of the things that you're seeing is the terminals buffer by lines. So when I'm typing a whole line, you don't actually see it until I hit enter, and then the whole line kind of goes in there. So with sort of a little bit of hacking, with this audio thing and Pi Audio and some other things, was actually able to get the Mac and the Superboard to kind of talk to each other just over a socket. So everything on the socket would do that. Okay, so this is just only the start. The thing that we just did here was like an initial prerequisite, right? It's like, well, if I'm going to do anything with the Superboard, I have to be able to communicate with it. And this is just the start of getting really insane at this point. So the next thing that happened with this, so this is what I'm showing here is something slightly different that's going on. So this is a little movie of something else happening with the Superboard. This is uploading some machine code. This is uploading essentially 6502 assembly code, or the result of some 6502 assembly. Looks something like that. There will be a quiz later on your 6502 assembler stuff. This was sort of an afternoon project where I actually ended up writing a 6502 assembler in Python 3 from scratch. And the reason I did, it's just absolutely amazing that you could do this in an afternoon with Python 3. It's 500 lines of Python 3. About maybe 350 lines of that is just a huge table of 6502 opcodes, which means that the whole assembler is actually 100 lines of code. It's 120 lines of code. Just amazing that you could do that. So there's essentially a Python 3 assembler. And underneath the covers, what's happening here is there was a little device driver that I wrote that I'll describe in a second, parsed through a Python 3 6502 assembler. It sort of made this file of hex over here, and that's actually what's being uploaded to the Superboard right now. So there's an upload process kind of taking place. Now, as far as what this is essentially a device driver that allows two-way messaging between the Superboard 2 and a client running on the Mac. So this is essentially, it's essentially something that's meant to do message passing. It sends requests, it allows control, sort of two-way communication. And it's something that's meant to coexist with Microsoft Basic running on the Superboard. So what's happening here is there is a small messaging driver that's assembly code coexisting with BASIC in only 8K of memory. So this is very, very memory restrictive. And what this is going to do, I'm going to tell you more about this in a second, but it essentially allows the user of writing BASIC programs on the Superboard to make outgoing requests. So this is what a request looks like. You can essentially set some basic variables. Okay, line numbers are making a return. Maybe not yet, but they'll come in Python later on, I think. So you have line numbers, you have some variables, and then this USR thing is an example of making a request. That driver will take that and then just blast it out the cassette port to this, some client on the Mac. And what the client gets to do, for lack of a better description, is distributed shared memory with the Superboard. Once the client gets control, it actually has full control of the whole memory of the Superboard, including the basic workspace of variables. So this messaging driver, this is sort of what it looks like when you do this. I have a picture where running a program and it sent out this request. What is happening here is I decided to use this as a vehicle for kind of getting out into the larger cloud. It turns out that you sort of have this messaging architecture where there's this driver on the Superboard. It talks over audio to this modem, and then there's this client sitting on the other side of a socket. And between these two, there's some kind of binary messaging protocol that's kind of taking place there. That's actually not so interesting, but some of the more interesting parts of it are actually what takes place on the Superboard. To do that, you had to figure out how to interact with Microsoft Basic using like undocumented routines. There are some resources for this, but you had to go into some very old documentation where people had actually reverse engineered the ROMs and told you like routines of things. You could find out like what the format of basic variables is in memory. You could find out things like how does this machine store floating point. It's not anything standard like IEEE, single precision or anything. It's some completely custom thing. So that's what's going on the Superboard side is a whole bunch of like really horrible device driver hacking and like reverse engineering of BASIC. On the client side, I started messing around with ZeroMQ. I decided this would be really interesting if I made this client just set up a ZeroMQ socket and then have that connect to the rest of the world. So what this does is when a request comes in from this Superboard, it hits this messaging client, and this messaging client actually just starts publishing requests on something known as a ZeroMQ pub socket or a published socket. And those just go out into the, quote, cloud. I don't know where they go. We'll see how this works in a second, but you end up just with this stream of requests kind of going out there. And the way that services interact with this is you can use ZeroMQ to simply subscribe to that feed. You can write a separate program that just, I want to subscribe to the Superboard request feed. These are programs that can just live anywhere. They don't have to be on the same machine. They just have to be anywhere that you can access with ZeroMQ. And then you just wait for requests to arrive. And then to kind of back that up, it turns out that this messaging client has a separate ZeroMQ socket that's used for command and control. So the way that this kind of gets set up is a request will just get broadcast out. Some service might subscribe to that, and then if it wants to respond, it actually echoes that request back to the messaging driver saying, hey, I'm going to respond to that. And once it responds, so this is kind of what it looks like. You essentially have code where you connect. I'm going to do a little demo of this in a second. But you essentially receive requests, you echo the command code back, and then once you have that, you get complete control over the Superboard. Essentially you get that distributed memory interface where you can like set and get memory regions, you can get and set basic variables. There's some response codes associated with it, and so forth. So here's kind of what that looks like. let me, I guess you don't need to see my video control here. So this is the initial setup if you've never used ZeroMQ. I've just said, okay, let's make a ZeroMQ subscribe socket. I'm going to tell this thing that I want to subscribe to requests corresponding to 37 space. That 37 was actually that USR thing that came back. And if this is working, what's happening here is I should just be able to get messages from the Superboard. So this is actually a message coming from the Superboard at this point saying I want 37.1. Actually, if I put this in a little loop here and I just say print, request socket receive over and over again, what you're going to see is that these requests maybe come in like once every second or so. So what's happening is the Superboard is just saying, and they're sitting there saying, hey, I want 37. Who's going to provide it? If nobody provides it, it just does this forever. It just constantly submits like a stream like that. So that's how requests work. To do the command, what you do is you're going to create another ZeroMQ socket saying that allows you to make requests. And so I'm going to connect this to a different part of the service here. And so if I want to respond to this, the way that this works is I essentially send a response saying, hey, I want to respond to 37.1. And it will come back and saying, okay, if you get that okay message, it means that, okay, you're in control of the Superboard at this point. So right now, this Python interpreter is in control of the Superboard. And what I can do, once I have control of it, is I can send it commands like give me the value of the variable a, for instance. It comes back and says, okay, a is 96.0. So this is actually this distributed shared memory thing here. If I want to get another value, like the value of b, I can get that. It'll come back. Okay, there's b is 42.0. If I want to change basic variables, I can do a set. I can say, okay, q is equal to 2. R is equal to 12, or something like this. So you can essentially just keep control of the Superboard doing this kind of like command and control thing. Keep in mind, this is probably a really horrible idea. I mean, this is like Python 3 is essentially directly controlling the memory of the Microsoft BASIC interpreter running on the Superboard connected over like audio here. So, yeah, like horrible idea here. So the command that I'm sending now is I'm telling the Superboard to return back to BASIC, and what you'll see is this is actually what it kind of looks like if you run this. So this is what it looks like on the Superboard end. The stuff down at the bottom is some messaging, and you'll see that it came back and like I don't know whether this is very visible, but I'm printing the value of Q and R. And it comes back as 2 and 12. So this thing essentially went out to the cloud, made a request, modified the basic memory, and then kind of came back. So this is kind of a big picture of what's going on here. I have this Superboard talking to this messaging client. I'm doing a whole bunch of ZeroMQ publish subscribe messaging where you can have services living anywhere. This can actually be written in any language. You're only sort of limited by what you can do with ZeroMQ. And then they can directly control this. How's everyone doing with that so far? Now, actually, there are some talks at this conference about ZeroMQ. By the way, I would definitely go to those. I mean, if you've never seen this ZeroMQ messaging before, it's really cool. Now, one thing that you might wonder is like, how did I actually do this demo? Okay, the machine is not plugged in up here. It's not even attached to my Mac. As part of this project, I created an emulated version of the Superboard. It turns out that you can dump all of the basic ROMs out the cassette port. And there's somebody that's this Mike Resny, I probably butchered his name, actually wrote a 6502 emulator purely in Python. I have no idea why. I mean, I don't know what the goal of that project was, but I found this, ported it to Python 3, and then just made an emulator for the Superboard. To do that, I'm not going to go through all the details exactly, but you have to know like what's the memory map of the Superboard, like where are the hardware devices. You have to know about keyboards, like keyboard grids. You have to know about video RAM. You have to know about like ACIA adapters. There's a lot of like low-level hacking, but the way that this emulator works, it's kind of cool. You just subscribe to different memory locations for reading or writing. So you just say, oh, I want to listen on this memory location. And then you can do whatever you want with it. And so you kind of build your whole emulator just doing this, like, the subscribing to memory locations. And so it turns out that demo that I just did is actually that. It's this is the Superboard emulated purely in Python 3, running on my Mac right now. So this thing is actually kind of the full Superboard. I mean, you can run little basic program. You got to love basic, right? You don't want to go back to basic. I'll just give you. I'll give you. Well, okay. I'll give you an idea of how fast it is here. Not super fast. Actually, the emulation is probably about 25% slower than the actual Superboard. So I could probably make it faster, but it's roughly the same. So a little bit of a sort of an emulation project, but that kind of opens up like a whole new line of thought. Like, well, what would you do with an emulated Superboard? And I think kind of know where this is going. I think you essentially make a cloud out of it. So I kind of took that and decided to make, well, there's a couple of components. One is just like a program storage area. And then there's sort of you could have machine instances of running Superboards, because you have this emulator, so you could just put them in like an emulation and then like make snapshots on it. You could have worker tasks that end up running these Superboards. You could have like multiple Python interpreters kind of hooked into this. And then you could kind of tie the whole thing together with some kind of data store. And so to do this, I actually played around with Redis, which is another very interesting project that if you have not seen that before, it's really cool. I mean, you might describe it as sort of like a key value store in some sense, but that's a really simplistic view of it. I mean, it has like dictionaries and sets and lists and queuing structures. And all sorts of really cool stuff. So Redis actually it's a C program. I mean, it's written in C, and then it has clients that are written in tons and tons and tons of other languages, like Python and Ruby and Lua and C#. So playing around with this, ported PyRedis to Python 3 to do this. And this is sort of a very nutshell idea of what it looks like to use Redis. You can create like a little, DB connection to Redis, and it literally is kind of like a key value store. You set and get values. You can do some queuing things, like you push data onto a queue, you pop stuff off of queue. So you can actually use this for, like work queue kind of things. So what I wanted to do is actually see if I could build like a cloud using this Redis thing. So what I wanted to do is be able to load and save programs, and I wanted to be able to do things like create instances, pass them input, do some shared memory stuff. And the really critical part of this is it had to be usable from the keyboard of the Superboard too. So I mean, this was like the really critical part. You had to be sitting at the Superboard too and be able to do all of this stuff. So you're gonna have like all this stuff sitting in the background. So this is kind of a taste of what's involved. The cloud service, because it can do this shared memory stuff, is actually able to directly manipulate the basic workspace on a Superboard. It can like pull out strings, programs, and settings, like essentially just rip them straight out of memory and like shove them into a Redis database. And the other thing it can do is take things right out of Redis and then just put them right back into the basic workspace. So you can almost think about this as like a context switch from like operating systems or something, where it's just from BASIC, you're gonna do a command, and then when you come back from the command, the whole environment is different. So that's what's going on there. And then as far as the instances of these superboards, they're not large. I mean, the whole superboard is only 8K of memory, has 1K video RAM, it's a little bit of CPU context. So there's a little Python object for this that just, you grab all that stuff out, you make it into a Python object, and then you just pickle it to Redis when it's not being used. So this is that's kind of what the instances are. These are the running superboard, and then to kind of make this work in the cloud. I think this is actually one of the cool features of Redis. If you haven't used it, is sort of the queuing features. Essentially, I could write these little runner programs where they would just connect to Redis, and they would just watch for something to come off of a queue. And the way that this would work is they would say, okay, I'm going to get some work. And once they got it, they would load whatever instance was in question, run it under emulation, and then when it was done, just save it back in the instance database. So it's kind of this little worker program that just gets work. It takes a little bit of input, and then you save it back in the database. And then some other things with this, it's actually set up where you can have an arbitrary number of these like runners. So if I wanted to create, like 500 instances of the superboard for some reason, I just have them all connect to Redis. I mean, I might have to think about like the scaling of that, but I mean, actually Redis can replicate itself as well. So, there's interesting, horrible, evil potential here. So instead of just sort of talking about that so much, I wanted to show a demo of actually what this looks like. So this is a little video of me typing on the superboard using this cloud computing service. So what I'm doing here is I'm just typing in a basic program. And the thing that I'm going to do next is I'm going to save this program off to the cloud. This is going to look a little bit cryptic, but what I'm doing is setting up a basic variable with a command S, which is save. And I'm telling this thing, go save the program hello in the cloud. So that's actually what's happening now, is this cloud service is ripping the program off the superboard and like shoving it into a Redis database. Just to kind of show you some of the things that are happening behind the scenes, I'm going to pop up a window. This is actually a little terminal window on my Mac that's showing some logging of the commands and stuff in the messaging. So what I'm doing here in the video is I'm typing in a new program, okay, that runs that, just counts to 10. And I'm going to do the same thing. This command that I'm typing, it's like $$ equals S count, is saving a program in the cloud. So I'm saving this as the count program. And what you're going to see is a whole bunch of activity up in the terminal here. It's essentially, this is this direct memory access where it's reaching in, ripping the program off the superboard and storing it in Redis again. Okay, what I'm doing now is writing a third program. So this is a program that takes some input. And what the program is going to do is just count the sum of a bunch of numbers. It's not a very interesting program, but it's sort of short enough to type in a demo. So you input n, it's calculating a total. You have to BASIC is very good about one variable letter name, like variable names, by the way. So I'm sort of keeping in the programming style of the era here. So I'm running that, and this is what this is going to do is it's going to count up to 1,000 and just sum things. So this actually gives you a little bit of an idea of how fast a superboard is. Not very, actually. Okay, so do a little calculation there. And again, what I'm going to do here is I'm going to save this off to the clouds. This sum is just saying save the sum program off in Redis somewhere. So here I made a typo, so I have to type it again. Okay, up in the terminal window, you see it kind of doing some messaging there. Doing these like peek and poke commands to directly manipulate the memory of the superboard again. Okay. Now what I'm going to do here, the next thing I'm going to do is actually restore one of my earlier programs. So the L command is just saying load this program from the cloud. That actually goes out to Redis, takes it back, and then just replaces the superboard with the program that I saved earlier. So what you're going to see here is now the old program came back, running. And so essentially, I built like a cloud storage system for the Superboard here. Now I'm loading the count program back, doing this. This is the stuff I wish I had when I actually was using the Superboard back in the day. Okay, there's that program. Now the next thing that I'm going to do is a little bit more interesting. This is what I'm showing here is how you create an instance of a Superboard. I'm basically saying create an instance called 1 of a Superboard. And what you're seeing over on the right is my Mac showing you a PNG rendering of the screen of the Superboard instance. So this over here on the right, this was generated by Python, and it's showing me this instance running. What I'm doing in the example is I'm loading the count program into instance 1 of the Superboard. What I'm doing in this next step is telling the Superboard that I want to list it. So I'm saying, okay, go list the Superboard. So keep in mind there's like 2 Superboards at this point. There's the one that's emulated on the Mac, and then there's the actual one that I'm running here. And what I'm doing over on the left here is just giving it commands, like this .1 I run is essentially the same as typing run in the emulated Superboard, and it just runs it. Okay. What I just did here, this C2, is creating another instance of a Superboard. And that's, okay, there's that. I'm using the Mac file viewer on these PNG images. So now I have 3 Superboards kind of going here. And I'm loading the sum program into the second Superboard. So this .2L sum is telling load the sum program into that instance. Here I'm just telling it to list the program so you can see it. Again, this is just an image rendering of that emulated Superboard. Now I'm telling it to run it. So this thing is going to run. And what's interesting here is that it's running and it's asking me for input, like this input n. So I'm actually going to supply that. This .2i 1000 is the same as typing 1000 on the keyboard of the emulated Superboard. And it's going to go run. Now, since this thing is running in the background, one of the things that I can do is request to pull variables out of the emulated Superboard. So what this command is doing is saying, give me the value of t from the running Superboard. It actually returns a -1 because it's busy at the moment. So there's a notion that you cannot manipulate memory of things that are running. Okay, I'm doing the same thing. Again, this is like pulling a variable out of the Superboard, and now I'm getting it over here. So to kind of summarize, like what's happening here, over on the right, an emulated Superboard is manipulating a value of t, did a whole bunch of calculation. I was able to kind of launch that and then rip the value of the variable back and put it on the console here. So there's kind of a little bit of like a parallel computing thing going on here. I mean, essentially you can launch things to these emulated Superboards, have them do calculation, and then pull it back. The final thing that's going on here as a debugging tool, there's a command to actually take the display of the emulated Superboard and show it locally on the real one. So if I'm trying to figure out what's going on, I can actually make it. I can see what actually happened on the instance there. It's a little bit slow because it's 300 baud. So now, so this is kind of so this is sort of the whole picture here. So you've got the Superboard, you've got modems, you've got ZeroMQ, publish, subscribe, Redis, stored instances, programs, virtualization. You can look at this and say, why in the hell would I spend my time doing this? So the answer on this is not that I wanted to use my Superboard. The Superboard was a pain in the butt. And to be perfectly honest, it went into the closet the second we got an Apple II. Okay? So, when our family got the Apple II, it was like, Superboard, see you later. I'm actually surprised that we still had it in the basement, to be honest. A slightly better answer, did it for fun. I love this system stuff, and I sort of viewed this as, I'm going to create the biggest most awesome mess of crap possible. Like, hardware, device drivers, signal processing networks, message passing, synchronization. Like, how do you debug it? How do you test it? How do you log it? I mean, this is great. Like, well, actually, deployment I have not really looked at because, the problem with like a fun project is like once you like if you take away the fun from any project, you're left with deployment. But the other reason for this is I'm pretty interested in Python 3. I just want to know, can you use Python 3 for anything? There's kind of this theme out there. It's like, well, nobody's using Python 3 and nothing like works with it. You can't port anything, and I just wanted to check it out. Can you use Python 3 on something super non-trivial involving a lot of moving parts, a lot of libraries, not Fibonacci numbers? Do something with it. And just see what happens. And so everything in this whole system was Python 3. It's using Python 3.2. And I think kind of the lesson from that is you can use Python 3 to do stuff. But I have to say it is a little bleeding edge. I'm going to talk about this in a second. But I mean, you have to know exactly what you're doing with like bytes and Unicode. You have to know how to port things. You have to know how to patch things. It is probably not for the faint of heart. But it is getting there. Just as a little experience on this, I ported sort of 5 libraries to Python 3, Pi65, PyRedis, PyAudio, PyPNG. Actually, ZeroMQ actually works with Python 3, but not 3.2 at the moment, unless they've patched it in like the last 5 days. So, and doing some of these ports, I wouldn't say that they're super hard, but you really have to understand bytes Unicode. I mean, like most of these ports were actually done over like an afternoon. By far, the hardest one that I had to deal with was PyPNG. This is a library that does PNG images. It's an old library, goes back to like Python 2.3, has a whole bunch of compatibility stuff in there, and PNG images are this horrible mess of like binary data and metadata. And it's like, if you don't have that bytes Unicode thing sorted out, it was really hard. I mean, it took a couple of days to kind of sort that one out. The other thing with Python 3, almost all of this code was pulled straight from GitHub or Subversion. It turns out that a lot of projects actually have Python 3 compatible ports sitting in either like pull requests or branches or forks. I was actually able to look at a lot of projects where it's like, well, it doesn't support Python 3, but then if you like dig around in the project, you'd find some like, some grad student or somewhere had like forked it on GitHub, ported it to Python 3, maybe made a pull request, and then the pull request is just like sitting there, waiting to go back into the trunk. So you can actually find stuff that's out there. Some other thoughts. I think Python 3 is cool. I mean, it took me a little while to warm to it, but having used it, I really like it. I mean, it's like, wow, I mean, it's really cool. It gets really better. It's getting better, especially the fact that I can type import NumPy into it. I don't know whether the NumPy guys are here, but I mean, that is great to have NumPy and SciPy in Python 3. And that's basically it. I think the main goal of this was just, try something with Python 3, do something sort of crazy. I think there's a lot of potential in Python 3. Since I'm basically out of time, I'd just like to thank people for coming. Brian Jones and I are updating the O'Reilly Python cookbook for Python 3. Look for that probably in late 2011. We're looking for recipes. We're trying to get experience with that. If you want to see this thing in action for real, like real hardware, I'll show you all the code and all this stuff. We're going to do like an after-hour session tonight, like 9 o'clock. So if you want to look at this stuff, it'll be fun. We'll try some things out. And that's basically it. I think do I have time for a couple of questions? Or?
We have time for about 2 questions. If you have a question, step up to the mic.
Is everyone speechless from the... there was no Gil, by the way. That's the... No, nobody's ready. But nobody's. I will swap anybody's iPad for this after the session. Okay. Do we have one question here?
Yeah. Thanks for the trip down memory lane. When are you going to bring the Amiga to the cloud? I saw an Amiga monitor.
You know, I don't know. I think my brother might still have an Amiga sitting around, but I don't know what the status of it is
Thank you.
at the moment.
Have you thought of submitting this to a museum? This would make an awesome exhibit, say computer museum.
Yeah, I don't know. Maybe. It's sort of too weird to. I don't know. Okay, well, I think everybody's ready for lunch, so just